Welcome back to another episode of Dave Does Math from Home. This is part 2 of our video on Stokes' theorem. Stokes is one of our flux integral shortcuts that we're talking about. In the first video, we talked about, let's talk about Stokes' theorem. Just a quick review of Stokes' theorem, because this bears repeating. Stokes' theorem says that the flux of the curl is the same as the circulation around the edge. So there's a lot of symbols happening here. It means if you need to take the flux integral and the vector field you're working with is the curl of something, you can instead do the line integral around the edge of your surface. This only works on surfaces that have edges. So if you need to do something on like a full sphere doesn't have any edges. That's not going to help you. And it needs to be like a smooth, continuous surface that has like an edge. So like half spheres are really good for this. Paraboloids are really good for this. Paraboloids always have nice little edges on them. And this Stokes theorem goes both ways. So in part 1, we did an example where instead of doing the line integral around a circle, we did the flux of the curl through the disk. And now we're going to do it in the other way. So this example is asking us to find the flux of the curl of f. So that matches. Flux of the curl of f through the positive surface of the paraboloid z equals 9 minus x squared minus y squared. So we have this paraboloid, this upside down paraboloid. It comes down. At some point, it hits the xy axis. So that's giving us a surface that's all above the axis. And that surface has an edge, which will be where it intersects the xy axis. And the surface doesn't go below the axis. That's the edge there, that circle. So instead of finding, if we were going to do this one without Stokes' theorem, we would first have to find the curl of f. So we would start by taking the cross product of this thing. And then we would parameterize this surface. And then we would find the derivatives and take another cross product to get the normal vectors, things that are always normal to this paraboloid. So things would be sticking out at various angles all over the place. We would represent that with n. We would take the dot product of those normal vectors, all the vectors normal to this surface, and the dot product of the curl of this vector field. We would do that, and then we would integrate that twice across the bounds from our parameterization. That would be the flux integral version of this. So when I first introduced Stokes, I said it was a shortcut. Here's the shortcut. Instead of doing all of that, we're just going to do the circulation around the edge of this surface. So the paraboloid hits the xy axis. The edge it makes there is a circle. So when it hits the xy axis, that means that z is 0. So we have this edge we have is x squared plus y squared equals 9. That's the path. That's the circulation. And to do this, I don't have to take the curl of f. I just get to use f as written, which is really nice. I'm into that. So we can just start the line integral process. Instead of doing this big nasty flux, we're just going to do the line integral. And the line integral is going to look like we need r. The path should be a circle of radius 3. That's 3 cosine t, 3 sine t. Yeah, let's use all three of these, comma 0. The path has no z coordinate. And then the derivative of the path will be negative 3 sine t, 3 cosine t, 0. And f. F is going to be negative y is negative 3 sine t. X is going to be 3 cosine t. 1. F dot dr is going to be 9 sine squared plus 9 cosine squared plus 0, which I think we can all agree simplifies into 9. So this line integral is going to be step 5. The integral f dot dr is going to be the integral of 9 dt. I guess technically there should be a dt here, and a dt here. Yeah, the integral of 9 dt, oh, the bounds, I forgot the bounds here. 0 is less than equal to t is less than equal to 2 pi. So the integral of 9 dt from 0 to 2 pi is 18t. Sorry, 18 pi. It's my bad. So this is it. This is the shortcut. Instead of doing the terrible flux integral over the curl of something, we can do this. And it involves 2 less cross products. So I think that is a substantial improvement. So I think Stokes' theorem is fun because it has the potential to improve things in either direction. And there are homework problems that do both of these things. There's homework problems that ask you to do the circulation instead of the flux integral version, and there are homework questions that ask you to do the flux integral instead of the circulation. So it's very versatile, and I'm told that it is used a lot in electrical engineering. So ask your electrical engineering professor about how to use Stokes in the real world. Don't ask me, I don't know.